So in our previous discussions, we've been focusing on the relationship between data points, where we're plotting the data points as points. In some cases, you want to display more than just points. You want to display shapes to represent the data, and in that case, you want to pack the shapes together. So here's an example called a word cloud, and this is basically the overview text from our data visualization course from the Coursera page. And I've just passed this through a web page called Wordle.net. And it created this word cloud, which basically displays the most common words, the words that are distinctive, that aren't everyday words like the and an. And then words that are used multiple times get displayed larger than words that are smaller. And then there's a process that packs these words into a collection. So instead of just displaying the words in order horizontally that you might see in a tag cloud, this word cloud is packed together. And there's a little spiral algorithm that it uses to basically find the first open space to pack a new word. And it tries to start with the largest words first and then packs in the small ones later based on that same spiral trial and error technique, spiraling out from the middle to try to pack words into the location that they'll fit into first. And so these techniques tend to use area as a measure, and we've looked at area as a measure before. It's a pretty good quantitative measure, but ordinal, it's not very good. Being able to tell whether two different shapes have the same area can be quite difficult. So if you have consistent shapes, it's hard to tell if I have the same amount of area in this blue circle as in this orange square. But if you have consistent shapes, if I have two circles, then I can tell that the areas are the same based on the length. And then if the shapes are aligned, if they share the same base, then I can just look at the height, at the position at the top, and tell if the orange circle is less than the blue circle in area. And so area is very difficult to determine, especially when you have inconsistent shapes, but becomes useful if you have consistent shapes and aligned shapes because you're using actually length and position. Also, area, as the area increases or decreases, the length is going to increase or decrease as the square root of the area. And so that also complicates figuring out a quantitative difference between shapes. And so if we want to plot a bunch of data without any coordinates attached to it, you can just pack the data together using, for example, area to display the data. So this is a Tableau plot of the population from our WDI database. And you can see some of the larger items are labeled if the label will fit in the region. But here the area is basically indicating population, total number of people. The area is proportional to the number of people, and because these are all the same shape, we can do a pretty good job of finding an ordinal. I can tell that China has more people than India. India has more people than the United States. United States has more people than Brazil, and so on. And so we get a good indication, at least ordinal or indication of the differences in population. And we don't need to use any other coordinates because we're just comparing areas to each other. We're not plotting anything horizontally or vertically. We're just using the horizontal and vertical axis to keep our shapes disjoint. So another way of plotting things horizontally or vertically is to display them in a map. And in this case, we've distorted the map into a cartogram. Here's an ordinary atlas of the world, and here's that same atlas distorted based on population, so that the amount of distortion, the area of the region, is proportional to its population. And you can see that certain regions have grown larger than they were before, and certain regions have grown to be much smaller. There's not very many people in Siberia, and so that's very small given its area. India and China have a lot of population, high population density, and so their regions have grown much larger. In Africa, you can see that Nigeria has grown to be quite large. And so this is a way of indicating with area certain data that you would want to visualize. Again, it's relative. It would be difficult to tell ordinally, if there's more people in, for example, France or Germany based on this display, because the shapes are different, and it's difficult to judge area relationships between different shapes. But we can certainly tell that Germany is roughly the same shape. It's just grown larger with a little bit of distortion than it was before. And so that's the distinction we're trying to make with the cartogram. So how do you create those cartograms? Well, you start in this case with a grid of density data. And this is an old algorithm for doing this. There's better techniques that are more sophisticated but also much more complicated. This is a nice way to do it. If you just fill a grid in with density data, such as your local population density, so within a unit, within some unit area, what is the population density? And so it could be heavily populated in this area and lightly populated in these areas. And so you create a grid like that of rectangular cells, and then you just scale each cell by that density value. So the squares that have a population density of 1/2 get shrunk by 1/2 in area. So that's about 70% horizontally and vertically. The areas that have population density 1 stay the same size, and the areas that have larger population densities would grow proportionally. So these squares would become twice as big, these squares become 3 times as big. And then you can see that what we had as a grid before now becomes disconnected. And so to reconnect it, we want to reconnect these corners to their average of the 4 corners that shared that corner. So we want to find a new point for this corner equal to the average of these 4 previous corner points. So we create a new set of grid vertices equal to the average of the 4 grid vertices that shared them before, or 3 or 2 depending on, or 1 if you're on the perimeter. And so we create this new grid, and this new grid is deformed. And so based on this deformed grid, we keep iterating that over and over until we get a final deformed grid, and then we look at the differences between the original grid points and their new positions in the deformed grid. That sets up a deformation. It basically tells us what direction we should move data points. And then we take our shape vertices of the outline data of our original map and deform them based on these arrows, and we can smoothly interpolate these arrows if we need in between values in order to create the cartogram. It's basically, we take a vector graphics representation of our data, of our map, and then deform the vertices based on this deformation to create the cartogram. So another technique that might be better than a cartogram is just the ordinary choropleth, and we see choropleths all the time. It's basically data that's plotted over regions of a map. This is that same population data, but plotted inside the outlines, the original outlines of our regions. In here, population is just given by the saturation of the color, and when we're looking at ordinal values, basically we can see that China has more population than India does, has more population than the US, which has more population than Brazil, and so on. And so you can you get a better indication of the order of these things from a choropleth than you might with a cartogram, because area is such a poor indicator of order, whereas density, saturation, hue, density being intensity of a color, saturation and hue are much better indicators of order. So there's several techniques now for plotting data without using coordinate data associated with the data for its layout. We're deriving coordinate data. In these most recent examples, we're using geographical data where we have maybe a region name or a country name, and then we're deriving the actual coordinates of that, perhaps an outline to fill in or a location on a map to generate, or we're using some other packing or layout algorithm to distribute the data. Those are all useful techniques in the case where you've got data that you don't want to use the explicit coordinates in the data as coordinates for their display.